All right, good evening. Can I start? I will continue recording, but for now there is nobody online. So maybe at one point I will stop in the future. So let me remind you what we have done. I also sent you a kind of summary a few days ago. So I don't write so much. At the root, we have a probability space. A probability space is a set, a family of subset of omega, and a way to measure a weight. So you associate a number between 0, 1 to each element of F, and you have some compatibility conditions. Now you should think about a random variable as a function from this space to this one, but in fact, X takes, associate elements of omega to omega to element of lambda. So it's a function from here to here, but you need the other things around. And you have some conditions. Think about random variable like a question. This is a description of a complicated system. You ask a question on your system, and a random variable is a question on it. Now, this has also some properties. It's a measurable space. Examples is either a finite set or countable set or Rn. And then I introduce this notion of expectations through one more function. So you take one more function from this set to this one. This one has the same properties than this one, but you can keep in mind that this is almost always either R or Rn or a set of matrices. And the expectation is given by this formula. So for F going from this to here, expectation of F is an integral over this space, f of x, this measure. In fact, when you write such an integral, it's a little bit misleading, but you should remember an integral is a limit of sums. And I just explained last time, it's not Riemann sums in general. This is what we call Lebesgue integral, but essentially, the construction is similar than for Riemann sums. It's a little bit more complicated. So this is a limit of sums. And you will see today why I prefer just to keep this set really open. I mean, I don't specify it because if I don't specify it, this formula can be used for many purposes. If you specify that it is R, like it is done in many places, then you have a problem when you define the expectation of a matrix or the expectation of a vector. So with this definition, you don't have any problem. There are two main types of random variables, what are called absolutely continuous random variables. So it's when this space is just Rn, and when the measure is what we say absolutely continuous with respect to the Lebesgue measure. So it means when in this expression, you replace this mu x dx simply by a function times dx. And this function is from Rn to 0 infinity. And it has a property that pi of x dx is 1. So it's a probability density function, PDF. This is the absolutely continuous case. The discrete case is slightly different when the image, so when this space is either finite or countable, so when the range, the image of this function is either finite or countable, then this mu x dx is what is called a counting measure. It associates to every point of this set a certain value between 0 and 1. So P is a function defined on this range, and it associates a number between 0 and 1. It cannot be up to infinity because otherwise the sum, I didn't mention, the sum of Px has to be equal to 1. So none of them can be bigger than 1. This is called the probability mass function. So the difference is here, you do a sum. Here, you would do an integral. The advantage of this notation is at this level, this notation is fine for everything. But when you specialize, it is either an integral or it's a sum. Yeah, I have written this. It's for you. I'm very ambitious for you, for all of you. I have prepared a lot of material for this evening. I hope that we can cover everything. But okay. And please try to read your notes before the next lecture. Otherwise, it's really difficult. I'm presenting a lot of things. Oh yeah, probably I have not written this last time. Sorry, the discrete one. But I don't think I have to write more than this. So when the range of X is finite or countable, of course, you need to remember on this set, we have also family of subset. So when it's finite or countable, you take all of them, all subset, all possible subset, which you cannot do in this case. But when it's finite or countable, this is called the power set. And I already mentioned last time, it contains 2 power n elements. So what is this n? Either it is a number of elements that this one contains, if it is finite, or if it is countable, it's n 2 power the set of integers. This has still a meaning, but it is a very big set. So this is a discrete case. So do you have any question about what we have done? So two types of random variables. Now in the notes, let me continue, and then I'm going to speak about 2 or 3 exercises. So what is good if you're in this setting is that we start with this space omega, which is the space of describing the model or describing your system. But let me add a remark. If we don't have this, so for any function, I'm going to keep the same notation pi from Rn to 0 infinity, satisfying integral of pi of x dx is equal to 1, or any p from either a finite set or countable set to 0, 1. So any function p from a finite set or countable set to 0, 1 satisfying sum of p of x is equal to 1. Both define a PDF in the first case or a PMF, because these are exactly the property that either a probability function or probability measure. PMF, what is the F? Yeah, function. Probability. Probability mass, sorry, this is a mass. Probability mass function, yeah. So either probability density function or probability mass function has exactly these properties. Which means whenever you have one function like this, it defines, I call it the law. It was exactly this, the law, this measure of a random variable. However, what is the problem if you start with this? The problem, and it will appear, the problem is we don't have this omega and also f and p. So what does it mean? It means you don't have the underlying system. This is underlying system. and this remark will become more clear in the future. It's fine if you have only one random variable. You can deal with it. But suppose you have two random variables, so two questions on a system. If you don't have the underlying system, but you just have the law, you face a problem. So I will show you later. But just remember, any function satisfying either this or this define a law of a random variable. The problem is that you don't have this underlying space. Now, I recall that you have to do something. I'm not going to present, but in the notes you have now 2 or 3 exercises, either about the Gaussian distribution. This is on page 25, 26. The one-dimensional or the n-dimensional Gaussian random variable. So I ask you, if you're interested to work on this, these are very standard exercise. You can find the answer everywhere. And there is one more exercise on page 27 about this. If x is a random variable, with a certain law, so with an absolutely, let's say, an absolutely continuous this is the simplest case. If it is an absolutely continuous random variable with law or with PDF, directly with PDF. Phi. And if you have phi a diffeomorphism, it is explained in the note, but probably you know what it is because I have already mentioned it. It's a function which is bijective, differentiable, and its inverse is also differentiable. I mentioned this is already in calculus 2. So if you have a random variable, absolutely continuous with a PDF, and if phi is a diffeomorphism, it implies that phi of x is also a absolutely continuous, random variable. And you can compute its PDF. Random variable. So this is a standard exercise. It's not difficult. In fact, it corresponds to a change of variable in calculus 2. So you have on page 25, 26, and 27, at least 2 or 3 exercises. I will mention a few others. Okay. Now, I want to consider 2 random variables. Because I want to deal with 2. So I consider a first random variable The point is they are both defined on the same initial space. So you have this space. You have the space of or the configuration of your system or all the possible things about your system, and you ask 2 questions. This is the idea. So suppose you have 2 things like this. They don't have to be the same. And be careful, I use this notation with the upper index, because if I use a lower index, it's a little bit misleading. We can think it's one component, which is also useful. But here, this means 2 different random variables. I could call them A and B, but okay, if I want to have n of them, I prefer this notation. And I'm going to consider is induced law mu1 and mu2. Remember, I have introduced this for any random variable. You have this induced law, which can be absolutely continuous, which can be of this type, but in general, it was defined. Or this is also called probability measure, or simply or law. Okay. Now I want to consider the two together. So I'm going to set, and I have to apologize for the notation, but it's a standard notation. Now I shouldn't use this letter for some clear reason, but it's okay, it's just one letter. I'm going to consider this as two components. So you can wonder, oh, what is this? I'm claiming that this is a function from omega to lambda 1, lambda 2. And just for information, oh, sorry, no. Lambda 1 times lambda 2. I don't think you have seen this already. This is called a Cartesian product. In fact, you know it. Because when you have first direction, second direction, and you consider the plane, it's exactly a Cartesian product with the first direction and second direction. So I will explain what is this. The Cartesian product. This is very simple. It's just two coordinates. It is a set of x1, x2. Again, I use upper and upper exponent because it can be a vector. This can be n-dimensional or whatever, such that x1 is in lambda 1 and x2 is in lambda 2. That's just a Cartesian product. You have two coordinates. But remember, a random variable is from this space to a space with a collection of subsets. It has the exact name, it's a measurable space. It's a space, Vic, don't sleep. It's not good time. You need to define a collection of subsets on this. So you can, again, guess the only way to do it. We consider Cartesian product is a collection subset generated by boxes. And what is a boxes? What is a box? It's simply one set in the first variable, one set in the second variable, and it's generate exactly this. This is a box. You have one, if in two coordinates, you have one interval in the first coordinate, one interval in the second coordinate, and altogether it makes a box. So more precisely, what is a box? Namely, it's denoted by A1 times A2. It is a set of x1, x2 with xj in aj. This is a box. But now remember, you need to do a measurable space. So you need this collection of subset of this has to be stable under intersection, finite intersection, finite union, or countable intersection and countable union, plus complement. So you have to play a little bit. You take boxes, you take complement, you take intersection, and you take union, intersection, and complement. And if you do this, we get a measurable set of measurable space. Lambda 1 times lambda 2, and this is a notation. So again, don't worry about this. This is simply you take boxes, you take intersection, you take complement, you take union. And in fact, this is exactly what we do on R. For the real line, when you want to define the set of all Borel set, you start with intervals, you take unions of intervals, you take complement, you take intersection, you generate a huge family of set, but then they are stable under the conditions you need for a measurable space. All right. So I just wanted to give you this framework. You have two random variables. Think about if lambda 1 is a copy of R, this is a second copy of R, you just get R2. Try always to keep in mind a simple example, but I cannot present only simple examples because we need to have a general framework. Okay, now you have this. Then this is a random variable. So it has an induced measure. Then the induced measure, I'm going to recall its property, its main property, and I have to denote it by mu. Z is called the joint measure because you started with two independent random variables, you create a new one, and by definition, it satisfies. And it will become clear with this property. The probability of the set omega satisfying for all A belonging to this family that you have just generated with boxes, it satisfies belonging to A. This is okay, let me make a picture. I do the picture like this. Think about these two coordinates, which are lambda 1, lambda 2. First, I generate this set lambda E1 times E2 by considering boxes of every type. Okay. And now we have one random variable. So it's Z is from the probability space to this plane now to this two-dimensional space, if we look at this picture. And the joint measure, so mu Z satisfy, take any set here. It has not to be a box. Take any set here. The probability that your system has a first coordinate, I mean that it satisfies the first coordinate, then the second coordinate is in A, so these are all the points here. Then this probability is by definition the joint measure of A. And I use this notation, but again, this is just a notation. This is a function 1 on this set A times this joint measure, and this is a notation for this joint measure. So you have to think about two conditions. These are like two conditions in your system. Probability that your system has a certain condition in a set and a second condition also in this set. All right. Now it will become more clear. This is a general formulation. In a minute, I will give what happens when both random variables are absolutely continuous. And it will become simpler. So one remark, and this is important. For any A1 inside this E1, and A2 inside A2. What about the probability of a set which has this shape? This is A2. Oh, sorry. If you think about it, this is lambda 1 times A2, and A2 would be here. I don't put any constraint on the first variable. I take all of them, and I put a certain interval in the second one. This is such a band. So for any A1 in E1, and I can also consider the other one. I can also consider something like this with a A1 here, and this set here is A1 times everything in the second variable. So we have what is the measure of A1 times this one? Can you guess? You have two questions, but you give complete freedom for the second one. So this has to be the same as a measure just of the first question. And the same if you ask, this is a Z. If you ask nothing about the first question and a certain limitation about the second one, this is mu x2 of A2. And these two measures are called marginals. Marginal measure. This is, you have two questions in your system, but you don't impose anything on one of these two questions. And then you find, yeah. Oh, yeah, you're right. I had to correct my notes as well many times. Yeah, so far I'm using always upper because remember, these can be vectors.
Also there, I think it would be A1 times lambda 2.
This, thank you.
Also the x2 on like the indices again.
This is x. Okay. Yeah, let me know whenever I do mistake. I cannot tell you how long I spent preparing this lecture. You will be scared. No, it takes a long time to make it precise in general. Now, special case. If lambda 1 is just n1, so it's a n-dimensional space, and lambda 2 is n2, and if x1, x2 are absolutely continuous, they're absolutely continuous. They have a PDF, probability density function, new x1, new x2. Oh no, pi. This is pi. Sorry. Pi x1 and pi x2. Then we write this mu z. In this special case, we write pi x1, x2 for the joint yeah, because I should mention if x1 and x2 are both absolutely continuous, z is also absolutely continuous, so you can speak about its PDF. And one has, now how do I rewrite these two things? We have new x1, no, sorry. Pi x1 of x1 is something you have certainly seen. Pi, you integrate over one variable. And you integrate over Rn2. I hope there is no mistake. And pi x2 of x2 is this integral over lambda 1. Again, I put upper exponent because these can still be vectors in R of n dimension, n1 or n2 dimension. And this is in this special case. So what is written here is just the general case. You know why I want to write this? Because this could be sum. I mean, if it is discrete value, we have sums here. So it's not very nice to say, oh, this is the case in the continuous case, but you just replace integrals by sum in the discrete case. It's better to have a general formula, which is valid always, and then you just take a special situation. Right? Any question or remark? So again, now we have two functions on the same space, lambda, omega. Like two questions on your space. You can think about you have you have a couple of dies, and you just ask two questions about the sum or about the value of one of them and so on. I want to come to correlation and cross-correlation and covariance. So this is, I write, okay, I write it in the continuous case. For xj from omega to nj, oh yes, and on this page, in this, we will see why one notation was very useful. Remember, I introduced the expectation for function of x. And I told you this function can take value. I just recall it was the f. It can take value. So it was from this to this. When I said this space, I want to keep it free because I want to cover all situations. But I mentioned it can be R, it can be Rn, or it can be matrices. Now, identity is just a function. Maybe I should mention what is identity. Identity of X is simply X, no matter if X is one-dimensional or n-dimensional. So if it is one-dimensional, this is a number, this is a number. If it is a vector, this is a vector, this is a vector. So what it means here, xj take value in R and J. So we have just this expectation. We are in this case. It's a vector. This is an element of R and J. So I define this expectation. For J is 1 and 2, and define the cross covariance matrix. Now I'll be exactly in the third case, cov x1, x2, and here when this is more general than the covariance, I found that, yeah, we can make it more general. The covariance for two vectors which can be of different dimensions, by definition, it is the expectation of these x1. Okay, let's check that this is well defined. Remember, this is a vertical vector. When you have one vertical vector times a horizontal vector, it makes a matrix. And it's a matrix which is, this is a matrix, or maybe I should directly write the result. This expectation, so everything is a matrix n1 times n2 of R. Everything is well defined. This is a vector minus a vector of the same dimension. You do a product with a vector, the transpose of a vector minus another vector of the same dimension. Altogether, this is a function. This is the f of x1, x2 that I have introduced in the general definition. And so the general definition holds for matrices. I don't have to adapt anything. I don't have to cheat. That's it. The cross covariance, why it's called cross? Because I'm not even asking that x1 and x2 are the same vector. Cross covariance is given by this. That's it. Now, if you put the same vector, so if we consider only one x, so if x is from omega to R, n the covariance matrix is simply cov of xx. Now it is an n by n matrix. If you put 2 times the same vector, it's a square matrix. You have this covariance matrix. And we just usually, when we repeat the x, I just write cov of x. This is a notation. Cov of x is just 2 times the covariance of xx. And now, if and I come back to the general situation, but so with x1 and x2, but I suppose that both are one-dimensional. Then we define so this is a standard maybe I should univariate random variable. This is the simplest case where the random variable takes only a real value. Then we define the correlation. Correlation of x1 and x2. Be careful, it's only defined when it's one-dimensional. But I can use my notation. It's curve of x1, x2, which is well defined. If it is a 1-by-1 matrix, it is just a number. And on the denominator, I can just write curve of x1 times curve of x2 square root. Okay, and this corresponds, if you can, in the notes, I have written a longer formula, but I don't need it. Everything is here. If I put 2 times the same guy, I get this. And if I look at the expression, it is the square of x minus its expectation, and then take the square root. And it turns out that this is a number between -1 and 1. So just one remark, mathematics should always take your hands and lead you to the result. So if you have the good notations, you don't have to think too much. You just follow the path. And indeed, if you have the good notation at the beginning for this, you don't have to wonder if it is well defined. No, this is the expectation of a matrix. There is no problem. Now, you have to be one-dimensional here because otherwise this would be a matrix divided by a matrix. This is not well defined. So you cannot do it if it is more than one dimension. Or maybe you can do it, but you need to give a definition by what you mean. It's possible, but you need to explain what it is. Any question or remark? Can you follow? Okay, if you have already attended the course on probabilities, this is the same, but I'm going just a little bit faster. Definition about independence. Random variables. Xj from omega to lambda j are independent if the picture is no more here. But the definition is quite simple. If for any aj inside ej, mu z let me do the same picture again. We say that the two random variables are independent if whenever you measure this, the picture is a little bit misleading because if you think about calculus 2, the surface or the area of a rectangle is just a product of the two distance. But okay, because x1 and x2 are independent in a sense. But if you look at the formula, I have written the probability that the first condition, comma, the second condition is in this rectangle has no reason to be of this form. But we say that they are independent if precisely when you measure this with a general formula for a joint measure, it is a product of the two measures. And now, let me just make the special case of absolute continuity. If we are dealing with PDF, it's just a product. So, remark. If xj from omega to lambda j. Oh no, then it's to r n j. Absolutely continuous. Whenever I speak about absolute continuity, I need to have this space here. Absolutely continuous. Then independence. Can be written, or it reads the joint density, probability density function is just a product of the two density functions. This is just a special case of this, but this formula also holds for discrete valued random variable or something more general. Not all random variables are either absolutely continuous or discrete. You can have mixture, you can have things more complicated. But of course, these two families are the biggest one. Okay. Now, I will come back now to the remark I made about if you have only the law and not the underlying system. I could skip it, but I think it's also interesting. And I'm going to, I didn't do a copy for everybody, but maybe just have two on this column. I will need this picture, and I cannot do it on the blackboard. This is too difficult. So just at one point, I will mention this picture, but I will not be able to do it. If you are online, this is the picture. But there is nobody online. All right. I know. So now, I just mentioned so far, both x1 and x2 were defined on omega. But what about if only mu x1, mu x2 are given? And in fact, this is a rather deep problem. And I will just, and this is related to what is called the transportation problem. Which is also a problem in optimization. It's a problem I mentioned on a course on graph theory. It's really something rather deep. Then in the, yeah, in the, oh yes, independence. It was a contraction. Okay, so let me just come back to this and rather quickly, please have, if you're interested, you can look at the notes. So this is a problem. Instead of having already x1 and x2, two random variables on one space, so two questions on a given system, suppose you observe your system, but you only have the two observations without knowing your system. So you only know these two probability measure. So what is the problem? And it's on this picture. So let me give a definition. It's a long definition, but I think it's good. Definition. Given two probability measures, I just call them mu1 and mu2 on the same space lambda, typically Rn. The coupling for them is a pair of random variables. So if it is a pair, I'm going to call it Z for x1 and x2. On a probability space. When I'm looking for a pair of random variables defined on the same probability space, such that you can guess the end of the sentence, so that xj is from omega to this has low mu1 and this is x1 and x2 from omega to lambda has low mu2. And still in the definition, we can add one more sentence. The joint measure z, because since you have you have this vector, you have a new random variable and you have a measure. So joint measure mu z is called, this is just an, it's called the transference plan. First, I thought it was a plane, but no, it's a plan. It's transfer. In the set transference plan. Okay, this is a capital I. Okay, so let me just explain a little bit with this picture, or maybe you can just finish writing. It's better than what I can do on the blackboard because it is in 3 dimensions. And usually on blackboard, I can hardly do it in 3 dimensions. So what you have, the 2-dimensional plane is what I did on the blackboard. You have a square and you have these 2 measures living on the edges of the square. So before I mentioned, this is lambda 1, this is lambda 2. Now we have the same space, so it's 2 copies of lambda. We are going to have one function living on this space, so you should represent it in 3 dimensions, and you only have what is called the marginal probability distribution function. So what is represented, the 2 curves on the left and on the right, are the marginal probability distribution function. And precisely, you look for the picture in the center, either the first one or the second one, which means you look for a function z living on the 2 copy of lambda, such that when you take the marginals, it follows either the first distribution or the second one. And as it is clear, more or less, and how do you get the 2 marginal distribution function? Remember, you integrate over 1 direction. So if you integrate over 1 line, you obtain, if it, depending on the direction, you obtain either the picture on the left or the picture on the right. Okay. So this is exactly, it corresponds to this definition. We have the 2 curves on the left and on the right, and we are looking for a pair of random variables, so to an underlying system such that its marginal probability distribution have these two given law. And of course, there are usually many solutions. And so the set of all solutions has this name. So one solution is called a transference plan, and the set of all of them is like this. Okay. This, maybe I should just mention where it comes from. In CS, now I'm on the website, you can find, on the second website, you can find several books. And I'm using this one on this picture is on page 47. Maybe I will add it in the notes. I will add this picture in the notes somewhere.
Sorry, but what's the rule all about? Like, how does correlation actually like affect the graph? Like, there's something about correlation.
Yes, but precisely I'm going to mention this. I'm just saying I have just given the definition so far. But of course, as I mentioned, you can have. Thank you. These two solutions, there are two solutions of the same problem. They do not look the same. So for some reason, we will see, probably one is better than the other one. But this is very much related to even what we did at the very beginning, you will see in a few minutes. Okay. As I said, I could skip this, but I think it's still interesting. Now, you can wonder if there exists always a solution. And the answer is yes, a solution always exists because you can make the two random variables completely independent. And then if they are independent, it means that mu z is just the product of the two measures. So the coupling, I don't give the details, but you can easily guess. The coupling always exists because you can choose x1, x2 independent. And then mu z is just the product of mu x1, mu x2. And you can check, and this is already done, if you integrate or if you take the measure of the entire set, you get directly the marginal measures or marginal distribution function. So this is quite clear. So at least this solution exists, but this is, I would say, the non-interesting case because the two random variables do not speak to each other. They are just independent. But at least you know that this set is not empty. It's not the empty set because at least there is this trivial solution. Now I'm going to just mention another special situation. And maybe we can see this situation later again. But it's very special. So another special solution, if it exists. It is, in a sense, no, yeah, this one is a completely independent solution. The one I'm going to present is, in a sense, less independent. So, definition. Same framework. I just write same framework. It's written in the note. Two measures, mu1 and mu2 on Rn is Rn. I just choose it Rn. Now, if they exist, and this is a very strong condition, if they exist phi from Rn Rn. The diffeomorphism again. So bijective, differentiable with the inverse, which is differentiable. Diffeomorphism. Such that integral f of x mu2 dx on Rn is equal to so look, this is a very strong condition. But it's a kind of situation when you have a change of variable. So when the two measures are linked like this, so in fact, if it's not surprising if a change of variable leads to the second one, and the second one takes into account the Jacobian, the determinant of the Jacobian matrix. So it's very specific. It's like a change of variable. Sorry?
What is mu1? Right hand side. F in the integral. F of phi of x mu1 dx.
Yes. Okay. Same framework. We have two measures. No, sorry. This is mu1 and mu2. No, sorry. So this is a 2, and this is a 1. So the same framework. So what the key word here, it means that these two measures are related by a change of variable. Okay, you need to make it a little bit more precise, but essentially this is the meaning. So when the two measures are very much related, they are not independent at all. Then, in this situation, then exists z given by x phi of x, which means the second variable is precisely this phi of x with transference plane, transference plan, z of x1, x2. I'm going to use a notation I haven't introduced. No, it's not correct. X1. Oh, there is a mistake in the notes. I put a comma, but it's dx1, dx2, I guess. So this on the blackboard is correct. Delta. Okay, what I haven't introduced, and I'm not going to introduce it now, this is the Dirac delta function, because this is just a notation, and I will write the meaning. Sometimes it's going to be shorter. So remember, my aim is to find a z, a joint measure, and I'm finding it, but I'm using this Dirac delta function. But let me explain how it works with this integral on f x1, x2, delta of x2 minus phi of x1. I'm explaining this joint measure is by definition, this is two copies. It's integral on one copy, f of x1, phi of x1, mu1, or there is a mu1 dx1. So, okay, what I'm saying, I'm just saying, if there exists a phi which has a very special properties, which mean that the two measures are very much related. And in fact, if they are the same, it is a special case. Then we have a solution to this problem I mentioned. It's given by this distribution here, or this measure. I haven't introduced, but this is exactly the meaning. When you integrate with respect to these two variables, you just replace x2 by what is here. So this is a meaning. I don't need to introduce. And this is called this solution. Called the deterministic coupling. Deterministic. If you want to forget these 2 pages, you can. But I mean, this transportation problem is a quite deep problem. I just tried to explain the statement. It's when you have 2 measures and you are looking for an underlying system which fit with these 2 measures. I gave the general definition. One solution is just to make the 2 random variables completely independent. This is not really interesting. Another special situation is here. And now let me state what is a kind of optimal solution, but I'm not saying that it exists. So more generally, and it will answer your question more generally, and there will be a problem for you. Unusually looks for a coupling is a special property. Coupling is a special property. And you will see that it will remind you what we discussed already 3 weeks ago. So definition. And then I will come back to something simpler. Yeah. Okay, definition. The transference plan. By the way, if you do some optimization, if some of you will do some optimization, probably you will hear again about this. Maybe in a simpler language, but it's related to this. So I put a star because it's a special one. A transference plan using star is a solution of the, okay, it's the name of 2 persons, Monge Kantorovich. Problem. For mu1, mu2 from Rn to 0, 1, 0, infinity with cost function. long statement. It's almost the end. So a special transformed plane is called a solution of the Munch-Kontorovich problem with a certain cost function, which is, there is a square, x1, x2 norm square. If nu z star is odd, okay, I know it's complicated, but let's just try to understand the statement. We know that we can find some pairs of random variables such that nu1 is a marginal function or marginal PDF, and nu2 is the other marginal PDF or marginal measures. But we want to find one which is with an additional property, and so finding these two random variables, we can look at this. x1 minus x2 is a vector in Rn. I take the norm. So this is a function. This is a function of x1, x2. Oh, I should write a function from Rn to R. So this is just a simple function. I can take the expectation, and I want to minimize this. So we are trying to find, if I come back to this picture, we are trying to find the function in the center which minimizes a certain cost function. And we have already seen this kind of things a long time ago, where we take the norm of a vector or the norm of a difference. So it has a special name. It's called the solution of this. I just wanted to mention this. And as I said, yeah, certainly it will play a role later on. And now exercise for Vic. Exercise. If n is equal to 1, which means if this is not a vector in Rn, but just one-dimensional, this problem corresponds. If your name is not Vic, you can also do this problem. This problem corresponds to a maximization of curve of x1, x2. This is not difficult. It's a two lines problem if you do it correctly. Minimizing this is the same as finding x1, x2, which has the biggest covariance. So it has it answers your question, what is the covariance? Why the correlation or covariance? This is almost the same. Why this correlation or covariance plays a role? It corresponds to this in one dimension. The solution of the initial problem here is the same as the solution of x1, x2, having the maximal covariance. All right, then I still have some time. I just want to introduce briefly conditional probability. Conditional probability in the discrete case is rather easy to understand. You have two random variables taking value in a discrete set. The conditional probability is one of them take a specific value, what happens for the other one? Now, in the continuous case, it's slightly more delicate, because if you have a distribution like this, the value at one point, or the probability corresponding to one point, is not important. You have to speak about interval. So you need a definition for what is a conditional probability in the continuous case. So I'm going just to give the definition. We can explain it, but I just take it as a definition. I have written just one paragraph about this. So definition. This is a conditional probability. What I'm going to define. So if, oh, and I can see a new mistake in the notes. If xj is from omega to r and j is absolutely continuous. Is an absolutely continuous random variable. We set phi x2 of x2 knowing x1 definition is going to be and just take it as a definition. I've never done any probability. It's the best way. I define a new function, which I denote like this. It's a function of two variables, but there is, in a sense, one which is going to be free and one which is going to be fixed. So I define pi x2 of x2 knowing x1 by this expression. And we understand, we know it is because we have two random variables. We have the joint PDF. We divide it by another one. Is there a question? Okay. And of course, I define this when the denominator is not zero. If the denominator is zero, I just don't define it. So it's defined only when the denominator, for the x1 for which the denominator is not zero. So we call it conditional probability distribution function. Of x1 of x2 under the assumption that x1 takes the value x1. It's a long name for this expression. And by the way, let me just mention, because I was a little bit confused. This expression is the same. You can check the definition. It's the same as x2, x1, x2, x1. Why is it the same? It's simply when you put two components in a vector, you can just switch the order if you make it coherently. So I put x2, x2, x1, x1, or x1, x1, x2, x2. This is just an exchange of the notation. Definition. The disintegration formula which is always valid, is maybe I take more space. Is I change this xn minus 1 x1 for xn. So I have not introduced this before, but in fact, there is nothing special. It corresponds to what I have introduced. If you call this at the beginning one random variable, it's just an iteration of what we have done with two. So this is two random variables that you put together, and then you just expand the second one again, you make it as two random variables and so on. So I introduce only this notation for two, but it's like having n questions on the system and you can just copy and paste everything. There is nothing different. The only thing is I'm careful about which order xn minus 1 up to x1, xn minus 1 up to x1. Now I'm claiming that this is pi xn of xn, knowing xn minus 1, x1 times, so times pi of xn minus 2, n minus 1, n minus 1. I'm claiming that this is always true, and you just check what I'm doing, because these conditional are always ratio. If you expand everything, you are going to have the same term everywhere on the numerator, on the denominator. So this is always true. It's just, but it's called the disintegration formula. And now there is a small exercise, which is very simple, but it involves both this notation and the marginal PDF. So in the above, in this framework, the framework introduced, we have the following equality. It's very simple. It's just a matter of writing the definition. And this expectation, I don't have to write it. Oh, no, sorry, there is a mistake. I should put a capital X2 here. X2. And this expectation is related to X2. This is quite clear because the expectation is always for a function of a random variable. Here, the only random variable is this one. It's an expectation with respect to X2. It's easy. The proof is just easy. But it links, here you have a conditional probability distribution function, and there you have the marginal probability distribution function. So there is a relation. Now let me just state a few exercises. Because it's difficult to make exercises on this, I'm going to give you a list of examples which are in this book. Oh no, sorry, I made a mistake before, I will correct it. You can just look at these examples, try to understand them, and write a report about them. So I call it exercise, but it's more understanding something. So you can prove this lemma. The first thing, look at examples. So 2.18, page 42, because this is related to what we discussed. And 2.26, 50. Sorry, I think I gave an incorrect name before. This is the book I'm now using, RC. And it is on this website. 50, good question, 50, I guess. But you can easily find. So it's related to what we have done. These are examples. So you you have to check something, but if already you understand, this is very good. Okay, we have 1 or 2 more minutes. Let me just introduce with some pictures what I'm going to do next week. I told you I don't want to spend too much time on mathematics. I want to come back to data assimilation. So at most next week, I should finish this mathematical part, but it's going to be more quick. We need all this. Remember at the very first lecture, we had a dynamical system. So we had this relation x at time n+1 was a function of x at time n, and maybe also explicit dependence. And the pictures, it was like this. If you start at the xn, you get a new point xn+1, and so on. And we constructed some synthetic data related to this. Now, and at one point, we also tried to find the best initial condition. But always it was 1 point. I was looking at the time for 1 point. Now we can slightly change our point of view. We can suppose the initial condition is in a certain set. Instead of saying it's exactly here, we can say, oh, it is in a certain set. Then we can look at the image of this set. The image of this set will be like this after 1 step. Probably after 1 step, it will be 1 more step, it will be like this. And we can now even associate some probabilities. So if at time n, it has a certain probability to be here, then what is the probability to be inside this one, and so on. So we are directly, once we think like this, we are directly using the language of probability that I have introduced. So this is now the motivation for what we have done. We want not only to consider 1 point, but to have a certain set and say the probability that the initial condition is here, and so on. And still, this is deterministic. The evolution is, if you have this formula, you can compute everything. But a more complicated situation is when you have a certain noise. So you have xn+1 is given by this deterministic formula plus a certain noise. So it means you are not going to get the red part, but you are going to get the red part plus some random noise or some noise, which is going to change the shape. Now, if you want to describe this properly, you need the notion of Markov chain or Markov process. This is it's a standard subject. You have 2 approaches, either discrete time or continuous time. I'm going only to deal with discrete time because the continuous time is more complicated, but just for information, why the continuous time is also useful is if you want to, Brownian. If you want to discuss Brownian motion, is it correct? Okay. If you want to discuss Brownian motion, which is something, it's a trajectory like this, or if you want to discuss stochastic process in economics, which are going like this nowadays, you need these Markov chains, but in continuous time. It's more demanding. I will not introduce this now. In fact, I'm thinking about doing 1 course about this in about 2 semesters. It's a difficult subject, so I'm not fully sure that I can do it. But so next time we are going to introduce Markov chain in discrete time, which is just an additional tool necessary for discussing this process. Okay. That's it. So we have finished section 2.1. And if you have some time, please just look at 2.2. There are 2 pages or 3 pages of blah, 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 trying to explain this picture. I will go very quickly on this. So, and then I will start introducing this properly. But the motivation, if you can read it, we will save some time. Thank you.